a 70-gallon aquarium. So I'm going to write that out for you. So the beautiful thing about having variables, which can be derivatives, is like it opens up a whole world of story problems for you. So you can have things that change or things that might be unknowable to be variables. So it's sort of like when you first started algebra, I don't know if you felt the power of saying, well, I don't know what this number is, I'm going to call it x. Here's a few things I know about this number, and you get an equation in x and you solve for x. This is like that, only Zilla. You know, you get to have a derivative can be one of your variables. You can say more things if you have a derivative as a variable. So here's my problem. There's a 70-gallon aquarium, and that's what this is. That's a 70-gallon aquarium right there. And let's say that I wanted to clean it out completely. So I have 70 gallons of tap water. Now I happen to know that my turtle, who's way over there, let's see if we can get a close-up of the turtle. The turtle's over there on the bottom of the tank. See him nosing around there? Okay, that turtle lives in the water almost all the time, and he needs minerals to keep his skin happy. So I'm going to be, what I actually do this is I'll clean out the whole tank, empty out everything, and then I'll fill it with tap water, which is not a great idea because it's not good water for him. And then every day bring in 3 gallons of well water, which happens to have, my well water has 1 gram per gallon of minerals. And the minerals are interesting. There's ferrous oxide, so it's basically rust. There's salt, of course, there's some salt in there, not a ton, and some other stuff. A lot of trace minerals, and it's good for him. Because if you think about it, turtles in the wild, they don't live in tap water. They live in murky lake and stream water with lots of dissolved elements in them. So he has happy skin because I bring in well water for him all the time. So let's say I put in 3 gallons per day of well water, and I take out 3 gallons of aquarium water. So if you can imagine, this is kind of a mixture problem. I've got 70 gallons of tap water. There's not a lot of minerals in there. There's chlorine, but it evaporates. It's not a mineral. So then I'm bringing in a mere 3 gallons, but I pour in the 3 gallons and I take out 3 gallons of the other stuff. Actually, it's the opposite. I take out 3 gallons to make room for the new 3 gallons. But think about it like this. It's as if I'm taking out 3 gallons of whatever the mix is and pouring in 3 gallons of well water, which has the 1 gram per gallon. All right, so what we'd like to do, here's my question. When will I have 49 grams of, and I'm going to call it big M for minerals. When will I have 49 grams of minerals in that water? How many days will it take? Now, if you think about this as just your average story problem, it's kind of perplexing because, okay, first day, 0 minerals, easy. Then I take 3 gallons out and I put in 3 gallons of the well water. So now all of a sudden there's some minerals in the water, but it's highly diluted because there's 70 gallons, only 3 gallons was well water. Then the next day I bring in 3 more gallons of well water and I take out 3 gallons of this diluted solution, and then I put in 3 gallons of the well water. And I do this every day. When will I get to the point? Because if you think about it, I'm taking out, when I take out 3 gallons of aquarium water, some of the minerals are going out. Every time I do it, after the first day, once I've added some minerals to the water, some of the minerals are coming out, but it's in the diluted form. So I should be gaining minerals every time because I'm putting in more minerals than I'm taking out. So here's how we do it. We set up an aquarium, or we set up an equation, not an aquarium. And the equation, I need to have a symbol for the amount of minerals per day. So that's M. And the change in minerals over time is equal to this, okay? So I add 3 grams per day, but I take out 3 times whatever grams are in there, because M is grams. M is grams over 70. So think about this equation. What it's saying is the change in minerals is equal to adding 3 grams, because that's what I bring in. I bring in 3 gallons. And then take away, I pour out 3 gallons of M divided by 70. So I have this many grams, whatever's in there that day, divide by 70. That's how many minerals per gallon. And I take out 3 gallons of that. This is the hardest part of the problem. Just getting that thing. Get that equation, and now you're going to solve. And it's going to be separable. I know it doesn't look like it is, but just think about it. I can rewrite that 3 as 210 over 70. And now if you look at it, I've got an M thing, a T thing, an M thing, and a constant. And a constant can be a T thing, it can be an M thing. That's no worries. So I can rewrite this just like I did the other one. I'm just going to exchange these 2 parking places. And I'm going to get a beautiful equation. And I'm going to have to write it where you can see it. So I'm going to rewrite it right here. So I'm going to have the dm divided by the 210 minus 3m, if I did it right. And I'm going to have the dt, I'm going to have the dt divided by the 70. And am I missing any minus signs? Did I mess up anything? No, it looks pretty good. Now you throw those integrals in front. And that's now we're actually able to do this. Now this is a chain rule integral on the left from Calc 2. Isn't it beautiful? So you take a -3 right there and a -1/3 out front. That guy's ready to go. And this guy's ready to go because that 1 over 70, it's just a constant. So this next line, I can rewrite over here, -1/3 natural log of the absolute value of 210 minus 3m, and that's equal to 1 over 70 t plus c. Remember that plus c. Now here's where we get to use the plus c real quick, because c is right here. If I wanted to try and solve for m now, c would get buried inside of some other stuff. Because if you want, eventually we're going to have to do an anti-log to get this natural log out of here. Which means I'd have like an e to the, looks like -3c over here. So now c is buried up inside of if you can look down that road, c would be buried up inside of a exponent somewhere. So I'd like to use that m of 0, m at time 0 is 0. Because when I started out, it's just pure tap water. No appreciable minerals in it. So I get to put in a 0 for t, right there. And I get to put in a 0 for m, right there. So let's see what this says. This says that -1/3, the natural log of 210, is c. Wow. -1/3 natural log of 210 equals c. Now I did that on my calculator. Let me see if I can find that real quick. It comes out to be -1.7824. If you're reading the book, they're going to leave it like this. You're going to be dragging that quantity around, because it actually works out to be later in the story problem, that 210 ends up being important. It pops in, and it kind of makes sense to you because it's 70 gallons, and 70 times 3 got to be 210. We're probably going to be dividing by 3 at some point because I'm putting in 3 and I'm taking out 3. So the 70 is going to get back in the problem somewhere. This 210 is going to be carrying around that 70 information. Anyway, but I've got C. So I'm gonna make a space, because here's my equation now. I now have an equation with no derivative anymore. I haven't solved, but I take this equation here. So I go back to the equation that has m and t in it, and I rewrite that number right there. So I have a -1/3 natural log, absolute value of 210 minus 3m equals t over 70 minus 1.7824. And that's where we are right now. Any questions? No, there's nobody here. But believe it or not, we're almost done. Because now all we have to do is solve for m. We get m equals. Technically, here's an equation that has m, and it's got t. We've kind of solved, but it's not very satisfying. So notice you're going to multiply through by -3. So you're going to have the natural log of the absolute value of 210 minus 3m equals -3t over 70 plus -3 times 1.78. I've got it. Hang on. -3 times 1.78 is, I believe, 5. Oh boy, which one is it? That's the 5.347. So notice it's this number times -3. So I'm going to get this natural log alone. I'm going to get this 3m alone eventually. So now we just put everybody to the power on e, because that's what's going to get rid of this natural log. So that side's going to be e, and this is going to be e to this big mess. And now we want to think of this as e to the -3t over 70 times e to the 5.347. Now let's do e to the 5.347 on a calculator real quick. And when you do it, it comes out to be 209.977. It's supposed to be 210. Do you see it? Do you see it? That's supposed to be the 210. If I were to carry around the exact value for C, I would have got this 210 back. So I'm going to count this as 210. I'm not going to write it as 29.977. It's supposed to be 210. So I've got this stuff here, the natural log. Oh, sorry, the natural log's gone. My fault. Natural log's gone. I have the 210 minus 3m is equal to 210 e to the -3t over 70. Let me get out of the way so you can see it. And now all I have to do is 3m to this side, subtract the 210 from that side, divide everybody by 3. Can you see it? I'm going to write above it, and we're going to get our final answer. Well, it's not the final answer, but it's going to lead to it. So let's recap what we did. We wrote a differential equation that captured a story. We used the facts of the case to solve the equation and get m equals. In this case, m is equal to, let's see, 210 minus, it's 3m. 210 minus 210 e to the -3t over 70. So dividing through by 3, I'll rewrite that. 3 goes, these two 10s become 70s, and we have a really nice equation. This equation kind of makes sense. The number of grams is equal to 70 minus 70 times this thing. So when t is 0, I have e to the 0, which is 1. 70 minus 70 is 0. M of 0 equals 0. It checks. But as t increases, this becomes a fraction. It makes that 70 lower. So 70 minus something less than 70. That's how many grams that I'm accumulating. This is a good answer. That's a really good answer. You can kind of see what it looks like. You could graph it and see what it looks like. It'd be a curve that starts at m equals 0 and goes up. But it's got a horizontal asymptote at 70 because that's the max. You know, as this t goes to infinity, as this t gets really big, this fraction becomes very small, cancels out that 70. I'm approaching 70 grams, which is 1 gram per gallon, which is what it would be if I filled the aquarium originally with well water. Are you with me? Think about it for a while. Now we got to solve the question. When are we going to hit 49 grams total? 49 grams in the whole thing. All you have to do is put the 49 here, and that's equal to 70 minus 70 e to the -3t over 70. So you're going to subtract the 70 that's all by itself. So 49 minus 70 is -21. So you get -21 is equal to -70 e to the -3t over 70. Divide by -70 and you get 0.3. 0.3 is equal to e to the -3t over 70. You're going to take natural logs because you're trying to solve for an exponent. So natural log of 0.3 is equal to -3t over 70. And if you solve the rest of the way, multiply by 70, divide by -3, you're going to get 28 days. Which is a very nice answer. That's a reasonable answer. Because if I was just pouring in 3 gallons a day, to get to 70, I would just do 70 over 3 days. And 70 divided by 3 is, 23 days, 24 days. So this takes a few more than 24 days. Because remember, I'm taking some salt or some minerals out every time I take 3 gallons of the old aquarium water out and put in 3 gallons of well. All right, well, that was a really boring session with you. What I'd really like to do is have a student or two here, because then we can joke around. We can have some fun with it. But that's your first video of the week. Thanks for tuning in.